Hello, everyone. Yeah, I'm Professor Lizzie Kendon. I am head of climate projections at the UK Met Office, and I'm also Professor of Climate Science at Bristol University. So through the many years I've been working, my focus really has been around developing and exploiting convection-permitting models in climate applications. So just for those who aren't clear, what do I mean by a convection permitting model? I mean models with a grid spacing of about kilometre scale, which means that they can explicitly represent convection on the model grid without the need for a parameterization scheme. And this is really a key development in our climate modeling capability, particularly in the context of capturing local extremes. So in the talk today, I'm going to cover a number of things. So I'm going to provide some information on how convection permitting models are providing new insights for local rainfall extremes, convective storm hazards, compound extremes, and also work that I'm involved in Africa, also applying these models to tropical cyclones. So as I've said, these models represent a major advance for our ability to look at future changes in these types of hazards. So they have a grid scale of less than 5 kilometers, which is compared to a traditional climate model, which has a grid scale of about 25 to 150 kilometers. You can see there's a huge difference here, and this is providing not only improved spatial detail and capability for hourly variability, but importantly are giving a much better representation of convective processes and feedbacks within storms, which is critical for capturing extremes of these type. I'm also going to talk a little bit about some work that I'm involved in translating the outputs from these models into actionable information for impact and adaptation planning. So I've got an example on work around flood risk assessment in the UK, another one about early warning system design, and for this to be resilient to unprecedented extremes in Africa, and also work through living labs to pull through science into planning. Okay, so I'll just make a start. So I'm going to start firstly with the work on the UK. So for those who aren't familiar, there was a set of climate projections at 2.2 kilometre resolution released for the UK as part of the UK CP 2018 projections. So this was really the first time we had national climate scenarios at these scales. So in this case, we had 12 members run for 100 years, so 1980s right out to 2080, under a high emission scenario, and they had a 2.2 kilometre resolution right across the UK. So this is really providing a lot of new capability around understanding how rainfall extremes will emerge through time, for example, and feeding into understanding of evolving flood risk. So one of the first results that I'd like to highlight is this one, which was quite a surprise when I first saw it. So this is simply looking at the frequency of exceeding 20 millimeters an hour across the UK. So I chose this threshold because it's kind of indicative of flooding, or certainly flash flooding. And along the bottom here is just a time series from 1980 to 2080. And the very thick red line is the average across the ensemble members. And you can see it basically shows a rising trend. So as we might expect under global warming, there's an increasing frequency of very extreme events across the UK. What is more surprising is the slightly thinner red line, which shows just one of the realizations that underpins that underlying trend. And you can see in this case, the red line jumps all over the place, but basically sort of tracks the trend, except it has this very sharp transition in about 2040. And although I did expect kind of obviously a lot of variability around the trend when you have an individual member, I certainly didn't expect such a rapid transition as this. Now, other members show similar jumps at different times. There isn't something peculiar about this particular member or this particular time, but basically what this is, it's a manifestation of the fact we've got natural climate variability interacting with an underlying trend. And so what happens is you can have quite a long period of time when nothing much is happening, and then you can actually get a sudden rapid transition like this, where a number of factors come together so that you have quite an extreme year. And following that, it seems that you shift into a slightly different regime of much more cases where we're getting these extreme events. And work that we've been doing has shown that actually this is down to increasingly more of extreme rainfall events occurring in clusters. So I guess the important message for this is that, how increases in local rainfall extremes will vary, and how we will realize those is not a simple picture of an increases year on year. Rather, there is a lot of variability, and it often is the case that extremes within a year occur in clusters, or extreme years with lots of rainfall tend to also occur in clusters from one year to the next. And this is really posing challenges for adaptation, because it's easy to misinterpret what we've observed up to now in terms of what's coming. But of course, if we were following the red line and we were in year 2040, we would have no inkling of what is about to come based on our past experience. The other thing to say is these results were for a high emission scenario, and they show about a 4 times increase by the 2070s in terms of the number of events. But we do get significant increases whatever scenario we follow, and for every degree of regional warming, there's a 5 to 15% increase in the intensity of heavy downpours across the UK. So we're going to need to be prepared for increases in heavy rainfall, whatever emission scenario we follow. So we've been doing some work with Bristol looking at other aspects of changes in rainfall extremes. So the first of this is work by Laura Devitt, and the first one I'd like to point out is this work looking at changes in seasonality. So there's 4 regions of the UK here: northwest, northeast, southwest, and southeast, and there's 2 kind of roses for each, one for the present day and one for the future. And basically, this is just looking at the occurrence of short duration extreme events in the different months of the year, with blue in corresponding to winter months and green summer months and so on. And so what you can see, if we just pick one of these regions, it's the same for all of them. So there's maybe the southwest on the bottom left. You can see in the present day, many of our extreme events for these short duration extremes generally occur in the summer months. But as we move into the future, certainly in the southeast, that's very clear. As we move into the future, there's a big shift to later in the year. And this is important because obviously, as we move later into the year, there is different potential for heavy rainfall to cause impact. Because, for example, there's leaves on the trees, or leaves are falling down in autumn and blocking drains. And so on. So there is this change in seasonality is quite important, and something that we may expect with the change in kind of convective activity in the UK. The other thing that we've been looking at is how changes in the spatial structure of events are changing. So this is looking at, in this case, short duration events in winter. Using these UKCP local projections. And what this is showing on the top left here, you can see that the composite of short duration events is basically becoming more spatially confined. So there's more localized and higher intensity. Now, this is also important because this is a change in rainfall that's not typically captured in flood risk assessment approaches. So typically what's happened with flood risk assessment approaches is that there is an uplift applied to observed rainfall time series to try and account for the fact that the intensity of rainfall has increased. But this doesn't really account for changes in seasonality, which I've just shown, and it also doesn't account for changes in the spatial structure of rainfall, which is clearly an important component of how rainfall translates to flooding. And you can see on the right-hand side here how different it looks. So the dotted grey lines show how rainfall intensity changes as a function of distance from the centre. If you just follow an uplift approach. So if you just raise everything by an increase in a percentage change in intensity, then of course you see intensity increasing right across the distance, radial distance. But in reality, the solid grey line shows that what happens, in fact, if you look at the projections in full, then there is an increase in the intensity at the peak in the center up to 15 kilometers from the center. And then there's actually a decrease in the intensity beyond that. So there's this change in the spatial extent of events, in this case in winter, which is an important component of any future change. The other thing we've been looking at is whether there's changes in the clustering of events. So again, we're comparing this with a standard uplift approach because this is what is used typically in flood risk assessment in the UK. So I'm just going to explain these plots. There's quite a lot contained in these. So if we just concentrate on the left-hand plots firstly, which are for autumn. So again, these are for the 4 regions of the UK. The blue bars correspond to the distribution of the fraction, so the number of events that occur in clustered. So how many rainfall events occur as part of a clustered event in the present day. And then the pink is the same, but for the future. And then there's also a black outline, which is what is the result if we just apply an uplift approach. So you can see that by definition, actually, the blue bars in this case exactly correspond to the black outline, because by definition, an uplift approach accounts for no changes in clustering frequency. Whereas in fact, you can see that there's a tendency in the future. So the pink bars shift to the left compared to the blue. So fewer of our events in future occur in clusters in autumn. And this is, I guess, likely to do to changes in the nature of rainfall. Presumably more of it is occurring as in more convective type rainfall, and less of the rainfall is in clusters. So that's an important factor which will affect the propensity for flooding. Now, in the summer, what's plotted is slightly different. So in summer, we see very little difference in the numbers of events, but what we do see is the difference in the contribution of rainfall from clustered events. So what is plotted in this case is the cluster contribution to seasonal rainfall. So basically, how much of our seasonal rainfall has come from clustered events. And so in this case, you can see that the uplift approach captures an element of this because there's relative changes in rainfall intensity across the distribution, but it doesn't capture the full signal. So you can see that the pink bars are much shifted to the right of the blue. So there's a big increase in how much clustered events contribute to rainfall in summer in all of the regions of the UK. And that is very much underestimated in terms of what would happen if we just looked at the changes in rainfall intensity. And it is these clustered events that have a really critical role in controlling potential flood risk. So is all of this important? So far, all the results I've shown you is purely looking at the rainfall itself. And what I've demonstrated is, okay, there's an increase in rainfall intensity. There's subtleties about how that will manifest through time, but also there are other aspects of rainfall that are changing, including its seasonality, the spatial extent of rainfall, and the clustering. Now, if we put all that into a flood model, how much difference does it make? And that's what we're looking at here. So this is work by Leanne Archer, who's a postdoc working with me at Bristol. And in this case, she's fed the results from UK CPE local through into the LIS flood hydrodynamic model to look at flood extent. So what is plotted here, if we just pick one of these histograms, which correspond to a particular depth. So, and then we're looking at the flooded area for depths of 10 centimeters, 50 centimeters, or 100 centimeters as a 30-year return period. Now, the red bars show the results if we put the full UK CP local rainfall data, the full time series data, through the flood model and pull out the results of the 30-year flood event. The bluer bars are the same thing, but if we only do an uplift approach. So we take the UK CP local rainfall data, and then we just provide an uplift, kind of trying to mimic the standard approach used in flood risk assessment. And you can see quite clearly the different shading corresponds to different time periods, with the light being historical, the kind of mid shading, the orange colors, and the mid blues corresponding to the near future, and then the dark red and dark blue corresponding to the end of the century. And you can see, if we just look at the dark red and the dark blue bars, there's a considerably more flooded area in the case where we're taking the full rainfall time series than if we use an uplift approach. So it's suggesting that the standard uplift approach underestimates the flood extent in the future, in part due to the fact that these are more subtle changes in rainfall that are missed by just simply looking at changes in intensity alone. So this is important in the context of how we want to design infrastructure moving forward. And I'm leading a NERC project called Future Flood, where we are exploring these results, and we're running a series of experiments to understand which aspects of the rainfall change. So is it the seasonality, is it clustering, which aspects are particularly important for capturing changes in flood risk. And we're also producing a whole set of new flood estimates for the UK through time from now into the future, which are full compound flood risk estimates. So they include fluvial, and coastal flooding contributions, and we can look at the relative importance of those as well. So that project is delivering over the next few months. Okay, so I'm now going to shift tack slightly and go. So far all I've been looking at is rainfall, short duration rainfall in the UK. I'm now going to look a little bit further afield, and also convective storm hazards. So the first piece of work I'd like to highlight is work by Abdullah Karaman that we're doing in collaboration with Newcastle University. And this is using the outputs that we have from kilometre scale models to really explore convective storm hazards. So this is things like hail, lightning, and supercells. So traditionally up to now, if we want to look at these sort of hazards, we've had to use a proxy of using the environmental conditions in traditional climate models. And they've typically given us indication that the changes in convective instability, for example, mean that we might expect an increase in lightning or decrease in hail. But actually, when you start to look at it in more detail and use all the much more outputs available from kilometre scale models, you get a very different picture. In fact, changes with the opposite sign. So in this case, Abdullah's developed a severe hail proxy, which uses things like Growlpool content, updraft strength in the hail growth layer, the changes in freezing level height and wind shear, outputs which are specifically available from these models. And it's using kind of this ingredients-based approach, which is inherited from severe storm forecasting. And this is allowing us to show that it's a much more complicated picture when we're looking at severe hail. So the bottom left-hand plot here shows the annual hail potential. You can see over the UK, it's quite low. And then on the right hand, and then the next plot shows the future change. And you can see actually, we're expecting here a decrease in hail in general, in terms of the European wide picture. And this is because which might seem counterintuitive, given that we're getting more convective instability, so more conditions, more favorable convective storms. But what is happening here is that the freezing level height is increasing. So actually the melting process means that it's much more difficult for hail to actually reach the surface, and that's accounted for in this proxy. But one thing that we do find, which is a middle panel, which is quite a surprising result, is that there's this shift to a different type of thunderstorms in the future. So what's shown here is just the distribution of freezing level height, and in grey is the present day distribution, and then in future is the pink. It's the pink distribution, and you can see we've now got this double peak distribution. And what this is telling us is that in the future we do have this shift to these warmer storms. These are storms with high freezing level heights, and actually these are akin to what we get in the tropics. And work that Abdullah's done has shown that these have a tendency to shift to the production of much larger hailstones, which actually do have the ability to reach the surface. So although we expect this kind of overall decrease in severe hail, when we look at significantly severe hail, so that's defined by a much larger diameter, there is actually an increase, particularly in parts of southern Europe. And some of this, the ability of these very large hails to reach the surface could extend to the UK. Abdullah's also been looking at supercells. These are responsible for some of the very largest hailstones, and they're very rare in the UK. Well, there's an example here just from last June. But there is evidence that these might be increasing in the future, and Abdullah's been doing some work on that as well. Some other work that we've been doing is looking at compound extremes. So we've been exploiting these models, again, European-wide kilometre scale models to look at this. This is work by Colin Manning with me and also colleagues at Newcastle University. So on the left-hand side, firstly, Colin's been looking at the potential impact of compound storms and the factors that come together. So in this case, he was looking at power outages from windstorms. And typically what is used at the moment is just using wind speed as a proxy for the amount of power outages you may get during a severe storm. But actually, in fact, there are a number of factors that need to come together to account for how many outages you get. And the important ingredients include the wind direction. So if wind is from a different, very opposed to prevailing, then you can get really large numbers of faults relatively to when the wind is in the prevailing wind direction. So that's one important factor. There's also rainfall preconditioning. So the wetter the storms, the increased probability of a large outage, essentially because this is down to wind throw, so trees falling on power lines, and they're more likely to come down when the wind is not in the prevailing direction, and also when the soils are wet. And then there's a final factor which relates to seasonal factors, and in particular the higher probability of large outages when there's a lot of leaf cover on trees. So there are important compound factors that influence the impact of a particular windstorm, and this includes the combination of wind, rain, and season. So we need to be able to capture these if we really want to look at impacts in the future. So moving to the right-hand side, Colin's then been looking at how we expect compound wind rainfall extremes to change in these kilometre scale models. So in this case, if you look at wind extremes alone, then there's only a small change. There's a big increase in rainfall, the severity from rainfall. And when you put these together and you look at storms that have both extreme wind and rain together, and you have joint extremes, then we see that there's quite a big increase. So what's shown here is the return period is dropping from something like a 20-year return period. Joint extreme is becoming just a 5-year return period. So there's a threefold increase in the frequency of these joint extremes. And so that's primarily driven by the fact that rainfall intensity is increasing in a warmer climate and there's more moisture available, but also there are subtle additional factors, and that's shown on the bottom right here, where Colin has looked at the change in storm tracks for these sort of joint extreme events. And you can see in red here where there's an increase, there's a sign of southward shift of storms. It means that they are coming across, tracking further south, and they are accessing much warmer moisture air than they are in the present day. So that is a dynamical contribution to this. That means that in the future we expect such a large increase in the frequency of joint extremes. And another work that's been done at the Met Office is pulling together many different components of the system at kilometre scale. So this is having not only just an atmospheric model, but also coupling with the ocean and tides and waves. And this is called the Regional Environmental Prediction System. And this is just one example of some results where you really need the kilometre scale to capture the coupled processes. So this is looking at meteo tsunamis. For those who aren't familiar with this is just a sea level disturbance caused by a storm, in this case a slow moving convective front that causes small disturbances on the sea height, but that can be important and lead to local coastal flooding. And this is a case where there was a meteo tsunami that struck in Portsmouth. And the observations in grey show basically the sea level. You can see the large coast, the large tidal element, but then you have this additional modulation which is due to the meteo tsunami, and that can lead to slightly higher water levels than you would expect just from the tidal range alone. And we are able to capture this now with the convection permitting model when we have a 10-minute coupling, which is the blue line. And the arrows here helpfully just identify the kind of peaks in this meteo tsunami, which just correspond well to what we see in observations. And basically what is happening is as the convective front transitions, there is a slow moving pressure disturbance, which affects the sea level height. And then that reflects back and forth across the coast in the English Channel. And that causes this kind of feature that we see. And we're now running long climate length simulations with the Regional Environmental Prediction System for the first time, which is giving us new capability to look at compound hazards at the coast and how they might change. Now I'm going to change tack for the kind of second half of the presentation, and I'd like to talk about some work we've been doing looking at tropical cyclones over Africa. So I'm leading a project called Repressor, which is funded under the CLARE, the Climate Adaptation Resilience Programme, through UK development funding from FCDO and the IDRC in Canada. And this is a really major project trying to improve resilience to tropical cyclones in Southern Africa. So in this work, we have the first multi-model ensemble of projections at kilometre scale for Africa. These are done through two groups. We have a new ensemble of projections run at the Met Office called CP for Africa, which are 4.5 kilometre resolution and span the entire African continent, which you can see there on the top left. And there are 5 members which are driven by different models from CMIP6. Then separate to that, there's the CCAM, which is a global stretch grid model, which is stretched to 4 kilometers over the region of interest over Southern Africa. And again, we have an ensemble of 5 of those driven by different CMIP6 models. And to combine, these are allowing us to explore some uncertainties in changes in local variables. In particular, we're focusing on tropical cyclones. Now, these models provide much more capability to explore particularly the most intense storms than we've ever been able to do before. So traditionally, climate models do not capture really intense tropical cyclones. They don't capture anything above category 4. Even some of the highest resolution global models that are in high-res MIP do not capture category 4 and above. So this is now we're able to capture some of the most intense category 5 storms with a much more reality. So what's shown here is in the animation is a historical example, a tropical cyclone Inawo that struck Madagascar in 2017. So the left-hand panel is the observations. So what's plotted is rainfall from GPM. The central panel is the CP for Africa run that's been done at the Met Office, in this case driven by the reanalysis dataset IRA5. And on the right-hand side is the IRA5 itself. And importantly, I should say that the CP4 in the middle has no nudging within the interior. So all it received is information at the lateral boundary coming in from IRA5. And then the rest of the simulation is completely free running. So the tropical cyclone evolves entirely as it wishes, interacts with the land surface and so on. So you can see here the tropical cyclone is spinning up. It comes in at the boundary. And then you can see how much more detail you get in the CP4 run. And also the intensity is much stronger than what's seen in IRA5. And you can see the nice structures within the storm all developing and spinning up, and it interacts then with the Madagascar land surface, decays its intensity, traverses down the spine of Madagascar, and then moves off. On the right-hand side is the time series of mean and minimum sea level pressure. The green line is the era 5, and you can see this is not able to capture the observed track on intensity, which is shown in red, whereas the CP4 run in blue really nicely captures both the timing and intensification of this particular storm. And this is really promising. And so we expect from these models, we're gaining some really new insights into how some of the most intense tropical cyclones might be changing. Also, there's other side to this. So those are kind of rapid onset events, if you like, but there are also slow onset effects. And in particular, we're seeing a change in rainfall associated with the changes in tropical cyclone activity. So the fact that we get an overall decrease in the frequency of tropical cyclones, although the most intense ones are increasing, has a really important impact for rainfall. And of course, this region is very much dependent on rainfall-fed agriculture. So you can see here, this is the contribution to rainfall from tropical cyclones. And you can see this is decreasing over large parts of the region. And in particular, in Madagascar and Mozambique, this is important because these systems are a major contributor to rainfall totals in the region. Now, there is some variability across the different models. You can see on the right-hand side there are plotted the same thing, but for the individual models. But there is definitely some consistency in terms of decreases over Madagascar. And this is important because it shows that not only do we need to be prepared for some of the most intense tropical cyclones making landfall, but also there's a risk of drought because rainfall patterns are changing and we expect lower rainfall overall. Now, these kilometre scale model results are being fed through into a compound flood hazard model. So this is the first time that we've been doing compound flood hazard modelling in the region. That includes both pluvial, fluvial and coastal flooding in a coherent way, and is also pulling through the new kilometre scale inputs to provide capturing tropical cyclones and looking how flood risk changes from the present to the future. So this is also work under the Repressor project being led by colleagues at Bristol University. So in this case, the model is called LISFlood, and there's been a number of developments to really enable us to do this. So there's been some novel approaches around getting information on the river bathymetry in the region. Coastal water levels are provided from a surge model called ADCIRC. And then the hydrological model is run at ECMWF, and that's providing rainfall runoff inputs into a river network, which is shown here on the diagram. And then over the region of interest, which is the hatched region where we're doing the compound flood modelling, this is a region of Mozambique shown there near Beira. And you can see in this case that gridded rainfall is also applied at this point directly either from era 5, as in the case we're showing here, or from the kilometre scale model itself. So in this case, we're just showing an example from tropical cyclone Idai, which impacted the region in 2019 and is the first tropical cyclone ever to lead to more than 1,500 people being killed in Africa. And this was due to very severe flooding in the region of Beira, which is in the hatch box there. And you can see in this case where we've got trying to look for the first time at the compound flood components. We've got the rainfall runoff on the top. We've got the storm surge shown there earlier on in the simulation, and then we have the rainfall inputs as well, and these are fed in then to look at how the flood develops. So in this animation you can see the results of how flooding is evolving, and it starts off with basically rainfall. Landfall of the tropical cyclone was on the 15th of March. And the first thing we find is that we get flooding in the floodplain. Here we are now, driven mainly by rainfall. And then from the 17th of March, which is now, we start to see evidence of the fluvial flooding becoming dominant. And on the 20th of March, the flood extent reaches its maximum size. And then after that, the floodwater starts to reduce. Now, important, if I just go back a slide, you can see with the storm surge that actually happened well before the peak of the flooding. And actually the storm surge happened in the neap tide. So actually its impact on this major flooding we see on the 20th is small. So actually in this case, coastal flooding was more driven by tidal effects than the storm surge itself. But with basically river flows being dominant in large parts of the catchment. But in Beera, which is on the right, just on the right-hand edge here, you can actually, the rainfall component was very important. So we can now start to look at an example like this of major flooding and understand the different components. Now, we have done some work validating the skill of this. This is here comparing the simulated flood against satellite observations. And we've looked at to what extent we are capturing flooding as predicted. Now the hits are shown in green, and you can see for a large part of this where the model is predicting flooding, indeed flooding occurred. There's some red regions where there were false alarms, and then there's also some very small regions in blue where there are misses. But in general, basically this is giving us good confidence that the model is doing well. I would say that the observations are not perfect here. For example, there are areas where there is vegetation and the satellite is not able to see flooding under the vegetation. So there is explanation for some of the false alarms, but overall the validation looks very good. So within Reprisa, we are trying to pull through the new understanding we're gaining both from the kilometre scale modelling, looking at changes in tropical cyclones, and ultimately the assessment of flood risk that's coming through the compound modelling through to decision making. And that is being led by the Red Cross Climate Centre through a process called Living Labs. So Living Labs are where different institutions come together to basically be exposed to new information. Scientific information is pulled through and they bring their own knowledge of the issues. And then the idea is through a common dialogue, a co-development process, then solutions are come together. So we have 5 different living labs within Reprisa, which are working on 5 different problems. So the first one is working with stakeholder groups on the design and dissemination of early warning systems, particularly the messaging, and to try and ensure this is more accessible to vulnerable communities. We also have a living lab around the production of impact-based multi-hazard forecasting. So trying to strengthen the national agencies in terms of producing impact-based forecasting, going beyond what is done currently. There's also work around stress testing plans. So in this case, organizational plans and early warning system design are exposed to potential storylines of future events, unprecedented events, along with understanding of growing vulnerabilities to identify basically stress points, gaps, and opportunities to improve systems and planning. There's also work around looking at organizational plans and assessing and creating these in a co-development process around making sure they're sensitive to both climate, but also conflict and migration dynamics. And the final living lab is around developing of adaptation plans and bringing through climate storylines and understanding from Reprisa. So this is really important aspect of the project. So we're not just stopping at doing the science and the flood modeling, but we're also trying to engage directly with stakeholder groups to pull this through into decision making and planning. Now, one of the things I mentioned there was about stress testing, and an important work we're doing to inform this is running things called counterfactuals. So in this case, we're looking at tropical cyclone Idai. And on the left-hand side, this is the track that tropical cyclone Idai took, and you can see that it made intensified in the Mozambique Channel, reaching high category 4, and then it made landfall at Beera, and that's where there was all that severe flooding, which I showed you. But through running the kilometre scale model with slightly different initial conditions and running it for a number of different cases, we can explore what IDI could have looked like. So in this case, it's exactly the same large scale conditions from ERA 5, but we're just setting off at a slightly different start time. And you can see we get many different possibilities on the right-hand side of what tropical cyclone could have formed and what track it could have taken. And some examples, like the bottom left there, look quite like what actually happened, but there are other examples where it could have been very different. So on the bottom right, it recurved and actually made landfall over Madagascar, which would have been called serious impact there and likely a storm surge. So we are able to use the models to explore what a historical event could have looked like. We can also transfer these into a future climate state and what tropical cyclone Idai could look like in the future. And this is a really important aspect of trying to stress test some of the systems in terms of ensuring that they would have been resilient and will be resilient to unprecedented events of the future. So I'm starting to kind of draw this to a close now. I just wanted to give a few more slides in terms of how we're translating reprise outputs into actionable information. So we're targeting 4 areas in the project. So one is around national level early warning systems and developing common alerting protocols. So thresholds that are appropriate as we move forward. And also are appropriate for local contexts. The other one is around stress testing of humanitarian planning. So this is where we are using these counterfactuals and storylines of unprecedented events and exposing those to systems and ensuring that if we can identify what the stress points are, what the gaps are, what the opportunities are. We're also developing climate storylines, and we're co-producing those and influencing organizational plans, including humanitarian programming, and also pulling through the new knowledge of changing tropical cyclone flood hazard and intersecting that with information about vulnerability and exposure to provide information on risk and pulling that through international adaptation plans. So these are the 4 kind of areas of output where we are hoping to influence as part of the project. Now I'm just going to wrap up with a summary and next steps, and then I'm happy to take any questions. So I've shown a lot here spanning the UK, Europe, Africa. In all cases, we're using kilometre scale models to provide new insights into changing hazards. And there are a number of examples where we're trying to pull that through into decision making. So both on the flooding in the UK and the example of trying to improve early warning system design and pulling through flood risk information into adaptation planning in Africa. So the key results are we expect more short duration rainfall extremes, important for localized flooding in the UK, so actually 4 times more frequent. But the years with lots of extreme events may be clustered, so it's far from the case of more extremes year on year. And we need to be prepared for this evolving envelope of plausible climate outcomes. Now, the standard approach in flood risk assessment is applying an uplift, so a percentage change, if you like, to the observed rainfall distribution to account for rainfall intensity increases. But that likely underestimates the flooded area, in fact, because there are other changes in rainfall, not just intensity increases, which I've shown. And under future flood, we're going to be providing new compound flood estimates for the UK. So, and then kilometre scale models are also providing new insights for changes in convective storm hazards, so hail, lightning, supercells, and also tropical cyclones over Africa. Now, these models are showing we need to be prepared for a category 5, so the most intense tropical cyclone making landfall over Africa, which would be unprecedented in the historical record. There is also potentially less warning time of approaching and developing TCs. So under the project Repressor, we are providing the first systematic assessment of flood risk from these storms over Africa, both now and into the future. Now, a key part of all of this is pulling through the new scientific information to ensure that it does have impact. And a key part or approach we're using within Repressor is using living labs to try and pull through the information into early warning design and adaptation options. And this is really, all our work in Repressor has shown that early warning systems will play a key role in reducing risk, but there are limits to their effectiveness given unprecedented events of the future. So there is a number of ways we can try and improve these systems, and I've identified a number of priority actions in the case of early warning systems over Southern Africa. And a final point here is about breaking silos. So this is ensuring that investment, so future funding in long-term adaptation, is harmonized with early warning systems, and the need to also recognize the inherent capabilities of communities to respond. So with that, just a final slide of where we're going at the Met Office in terms of planning for kilometre scale modelling. So we have plans for a major update to the UK climate information. So I mentioned quite a bit about the UK CP local projections. So we will be updating this, providing CMIP6 downscaled information and a broader package of information that goes right through to impact and improving the consistency between the different products. I mentioned the regional environmental prediction system. So there's new capability going to be coming from coastal hazards and marine heat waves. We're also moving now to not just regional models, kilometre scale, but globally. And these will allow us to understand the upscale effects of the explicit representation of convection. So not just the impacts on local hazards, but how they upscale in terms of larger scale modes of variability. And what we potentially are missing through a regional modelling approach. And then finally, we're doing work around exploring the potential for machine learning emulators to augment what kilometre scale information we have. So the top right plot here shows winter projections for the Alpine region. The kind of red shaded region is the space. So we have temperature changes on the bottom and rainfall changes on the vertical axis. And the red shaded region shows the range of projections from global models. And then the colored kind of squares show actually the bits that are sampled by kilometre scale projections at the moment. You can see we're really undersampling the total space of uncertainty here. And the hope is that through building machine learning emulators that we can start to fill out the gaps. So give a much better estimate of uncertainties at local scale. And with that, I will stop there and I'm happy to take questions. I'll stop sharing my screen. Thank you.